Welcome to our Practical Stats video titled Matched Pair Tests with Nondetects. This is one of a series of free videos. This afternoon we're going to look at these types of tests when you have data that are paired and how they are analyzed when you have data with Nondetects. The objectives for today are to inform you of the challenges of computing tests like this. Tests for paired data when there are Nondetects, and inform you what methods are available for these types of tests. And there are methods available. If you'd like more information, there is much more information in our course on handling Nondetects called Nondetects and Data Analysis at this same site, practicalstats.com. All right, let's begin. Matched pair tests are in the situation where you have two groups, group X and group Y, and the observation number 1 in group X has some natural relationship to observation 1 in group Y that it does not have to the other observations in group Y, so that these observations are paired in some sense. There's a direct relationship between them. And so the methods that we're going to be using will be taking the value for the observation number 1 in group X and subtracting off the observation number 1 in group Y to form a column of differences out here on the right. And the statistical tests will be actually on the column of differences. This is a good thing. This is called blocking in statistics. And what it does is to block out the extraneous noise that you do not care about. And so what you do not care about are the row-to-row differences. What you are interested in are the differences between the two columns. So actually data collection is often done this way just naturally by common sense. And that's a good thing also. So for example, if you had data from an urban area and data from an agricultural area, and maybe you were measuring concentrations in stream flow or in a well, and there were seasonal differences. And so you would go out and probably measure the value at the urban area in January and also measure it in January in the ag area. Do the same in February, the same in March, the same in April. And with these types of tests, matched pair tests, you would not be comparing the urban value for January to the ag value for April. Perhaps there's snowmelt or early spring rainfall in April, and so the fact that the ag sample represents that time of year is not a fair comparison to an urban sample that's not at that time of year, when that same type of event was not occurring. So time is one of the primary blocking characteristics in environmental science. Location is a second type of blocking characteristic. For example, we had some old method, either the field method collection or the laboratory method for analysis, an older method and a newer method, and we wanted to see if there was a bias, if there was some consistent shift up or down. If there were not, that would probably be a good thing, and you could use the data, put it all together, and analyze it as one set of data. If there was a bias, you'd have to try to determine how much that bias was and perhaps correct the old method to get it up to the new method scale or something like that. And when you do this type of approach, often these wells here or the sites have different characteristics, and that's by design because you want to see how this method change is a function of different characteristics of sites. And so the well 1 might have low concentrations, well 2 might have very high concentrations. We don't really care about the low to high concentrations in the wells. We just want to know whether they give you the same number with the new method. And so by doing this blocking, you block out those well-to-well differences. Other common examples of doing this in environmental science are up gradient and down gradient sites, or upstream and downstream sites, above and below something on the stream. Pre-event and post-event So the two columns would be different time periods. Maybe before some dramatic thing happened, a huge flood or a fire in the watershed. Or perhaps it's just that the first column has old data collected 10 years ago, and the new method has current data. So all of those are common situations where you would use a paired type of test. We're going to look at 4 of these tests briefly. The first one is a parametric test called censored paired test, and it will be a test for whether the mean of the paired differences equals 0. In other words, is the average difference between the two columns 0? The sign test is a non-parametric test. The signed rank test is a non-parametric test. And the paired Prentice-Wilcoxon test is a non-parametric test. And all 3 of these have similar, though not identical, null hypotheses. They are tests for whether the signed test is the median of the paired differences equals to 0. The signed rank test and the paired Prentice-Wilcoxon test look for whether there's a difference in the set of percentiles in the first column versus the second column. So an example data set is mercury in soils that was measured at the same sites in 1996 and 2001. In between those two was a major fire. This was in a national park, and it was a USGS study of concentrations on soils. So these measurements are blocked by location. They went back to exactly the same sites in both cases. And so that minimizes the causes of change due to any differences in geography, any difference in soil type across the study area. And so the differences that are observed are attributed to the differences in the 2 years, and that's attributed to the effect of the fire. You could have 2 different questions that you ask of this data, and depending on the question, you would choose either a parametric test on the mean or a non-parametric test on a percentile. The first question: is the mass of mercury over the site before the fire different than after the fire? That's a parametric test. The mass is something that you would sum all of the values up across the entire site to get the total. If you sum them all up and divide by n, you get a per site measure of that total, which is the mean of the observations that you've collected. So by using a mean, you're really doing a test for differences in totals. And this is especially true because you have the same number of observations. These data are paired, so they have the same number of observations in 1996 as they did in 2001. So you really are testing for differences in the total. The second question that you might ask is, do the concentrations seem the same, similar, before and after the fire, or is one of those time periods consistently higher or lower than the other? That's a frequency kind of question, and so that would be analyzed by a frequency kind of test, which is what non-parametric tests are. So here are the data. We have a column of concentrations in 2001, and I don't remember what the X was for, but it's there. And then a column of concentrations in 1996, and then for each of these we have an indicator, true, false, where true is the statement about whether these data are censored, whether they are representing a value below a detection limit. So a value of 0.02 here with a true would be a less than 0.02. Statistical programs like numbers, they want numbers. They're not going to read this less than sign as something that they can deal with. So I've added it on here just to make it more clear. But in the data set you would actually have 0.02 and then a true to indicate that this is a less than 0.02. As opposed to the second row, where in 2001 you also have a 0.02, but a false, meaning it's not censored, which means that this is a detected 0.02. And detection limits are technically values that are less than 0.02, so the lab can, and often do, report numbers at the detection limit for you that are detected. So what we want to do is compare a less than 0.02 here to a less than 0.02 here. For the parametric methods, we're going to need to compute those differences in a way that gives them the minimum difference and the maximum difference they could possibly be. And so if in 2001 this value were 0, that less than 0.02 was a 0, but in 1996 it was a 0.02, then it would be 0 minus 0.02, which would be a minus 0.02. But if it had been actually a 0.02 in 2001 and a 0 in 1996, it would have been a positive 0.02. And any values in between those would give me values in the differences between those two extremes. So we can compute the range of possible values with censored data and have two columns that represent the differences. Here there are two falses in the second row, and so those are two detected values, so it would just be 0.02 minus 0.021 gives me a minus 0.001, and that's true both for minimum and maximum. And so when these numbers are the same in the min and the max, that just means it's a constant, which means that we had two detected observations. We can do things like compute box plots for these individual columns, and we can see here that the data in 2001 appear to have a difference, at least in frequency, that's somewhere above the median, above the 50th percentile, because I don't see the line in the middle of the box here. The upper part of the box is shifted up in 2001 than it was in 1996. Some of these sites, it appears, have a higher concentration than they did back in 1996, but not all of the sites. We do need to be careful that these box plots do not show the effect of pairing of the samples. So I'm not really seeing here a picture of what is being actually tested, which is the differences. But in general, it looks like 2001 might be a bit higher in the upper end than 1996. All right, our first test will be a non-parametric test. It's the sign test. So the null hypothesis is that the probability of getting a higher number in 2001 than in 1996 is 1/2. Half the time you'd expect 2001 to be higher, half the time you'd expect 1996 to be higher. And if that's true, that they're half and half, then the median difference is going to be 0. The alternate hypothesis is that is not 1/2, that probability, which means it could be more frequently higher in 2001, or it could be more frequently lower in 2001, and you're looking for both departures from equal, and so that's a two-sided test. Alternatively, you could specify a single direction and say I'm only interested in the case where 2001 were higher than 1996. That's called a one-sided test in statistics. When would you do that? When you had some pre-knowledge or expectation of what the direction might be that you're interested in, and you have no interest in the other direction, because this test is going to completely ignore any evidence that 1996 was higher than 2001. So you only do this based on the objectives that you have. You should be able to state this before you ever see the data. And if you do know that, there's some thing that would have to be done if they were higher in 2001 than 1996, like some sort of remediation. And if it was lower in 2001 after the fire than it was back in 96, then you don't care. Then that would be a situation where you might do a one-sided test. I'll just be doing the two-sided tests here just to show you the different types of tests. The important thing about the sign test is it does not look at the number of the difference, the magnitude of the difference. It only looks at whether it's a plus or a minus. Which of these is higher than the other? So if we did this with some data here, this is not the same as the mercury data, just for a minute. Just some cases here that you might see. If you had less than 0.05 comparing it to less than 0.02, well, you don't really know which is higher. So that's a tie. It's not a plus and it's not a minus. If you had a detected 0.05 and a detected 0.021, well, you can make that subtraction. 0.05 minus 0.021 is going to be a positive number, and so that would be a plus. 0.05 to a less than 0.02 is also going to be a positive number. You don't know what the magnitude is exactly. It would have to be a range, but we know that it's a plus. 0.03 to a less than 0.05, because 0.05 is higher than 0.03, we really don't know whether that's a plus or a minus, so it gets a tie. You get a fair number of ties in this kind of situation, and that is an issue for the sign test. The standard sign test assumes that you do not have any ties. So back to the Mercury data now. There were 82 rows. 55 of those showed a plus sign, where 2001 was higher than 1996. 8 of those rows showed a negative sign, where 1996 was higher, and 19 were ties. A lot of those were due to the less than values, the nondetects, in one or both of the columns. So this is a fairly large proportion of ties. Again, the no correction for ties result that I've put here is how the sign test would be computed if you just used ordinary software that did the sign test. And what it does is to take the number of pluses and then compare that to the number of minuses and completely drop out the ties. So you would be saying, what is the probability of getting 55 pluses out of 55 plus 8, so 63 total events? 55 out of 63 does not sound like half and half. So it's going to be a strong rejection of the null hypothesis. But that's totally ignoring these ties, which are evidence for the null hypothesis, evidence for these two being the same. And we've thrown that away. So you cannot do that with censored data. So there is a correction for ties done back in the 1980s, I believe. The Fong correction, and it would give you a corrected p-value of 0.0013. So you see it's readjusted that very low value for the fact that we have evidence for the similarity of the two columns. So this is not quite as low. So this would be the appropriate p-value always to use with censored data. The second test, also non-parametric, is the signed rank test. And here the difference between this and the signed test is that you're looking at both the magnitude as well as the plus-minus pattern in the data. Bigger differences have more weight than smaller differences. They're stronger evidence that the two columns are different. So you're going to be computing the differences, x minus y equals d, ranking those from smallest to largest in absolute value, not just by themselves, but in absolute value. So a -5 would have the same rank as a +5 in terms of a difference. So it's the distance out from 0 in either direction. And then after you get those ranks, put a plus or a minus back onto them equal to the sign of the d itself, the difference itself. So these are the signed ranks. So the null hypothesis is that the median difference is 0, or you could say that the two groups have a similar pattern of percentiles. The alternative hypothesis is that it's not 0, or that the CDFs are not the same. Those are statements of a two-sided test. And then finally, you could specify the direction ahead of time to only one of the two possible ones. The signed rank test generally has more power than the signed test because it uses the magnitude of differences. It also requires a correction for ties. So the classical test, developed I think back in the 1940s, assumed there were no ties. And there is a correction for ties. In fact, there are several corrections for ties. The one that's in R is called the Pratt correction. There's other corrections that have been proposed. The question is this the best one? I haven't seen a good article that compares these tie corrections, so I don't know, but it's the only one available. with a p-value that is small as this one, and I did not in this case even print out the uncorrected value. With a p-value that's this small, we would certainly reject the null hypothesis and say that these two groups of data have different percentiles, and in general 2001 is going to be bigger than 1996. And I would know that just by looking at their medians. We would state that the two years are not the same in terms of their concentrations. And we saw a picture of that a few slides ago with the box plot. The third and final test that's non-parametric test is called the Paired Prentice-Wilcoxon test, or the PPW test. And it was developed in 1987, so much more recent than the previous two. And it has some important differences. It has a similar goal, similar null and alternate hypotheses to the signed rank test, to look at the CDFs and see if there's been a shift up in percentiles from one group to the other. It has more power than the signed rank test and the sign test when the differences are not symmetric. And environmental data are often skewed, and their differences are often skewed. So we often have this asymmetry. So that assumption of symmetry is a problem with the two previous tests, and it is not a problem with this test. It has a good pedigree of theory as part of the class of tests that are used in censored data. I won't go into that in this talk, but linear rank tests on Prentice-Wilcoxon scores. And you'll just have to take my word, that's a fairly standard procedure with censored data. It's built to handle ties, so it doesn't need this retrofit corrections that the other two tests do. It can be thought of as something like a paired t-test on the scores. The scores are kind of adjusted percentiles, where the percentiles are computed by throwing all the data together, computing their percentiles, then splitting them back out into the two separate groups, and seeing how they are different for the pairs. So in terms of power and theoretical justification, I'd rank the usefulness of this test as being higher than the other two. And generally, in terms of my preference of use for them, the paired Prentice-Wilcoxon, you would use that before the signed rank test, because I'm a little uncertain about that correction for ties, and it is an after correction. So, and same for the sign test, and usually the data that we collect, those magnitude of differences are important, and the sign test does not use that magnitude. So that's my preference ranking. You can do this in R with the ppw test command. It is not in the regular part of R, it's in the scripts that are right now in the course, Nondetects and data analysis. So you can see the output looks very similar. Its p-value is pretty similar to the signed rank test in this case. And also reports back to you the median of the differences. So with this p-value, we would reject the null hypothesis. We would state that the mercury concentrations for the 2 years are not the same. And since we put in 2001 in first, it's going to compute 2001 minus 1996. And say that that's a positive difference of 0.015. I believe it's micrograms per gram of mercury in this study area. All right, now a shift to a parametric test. So this is a test on means, which is quite a bit different. It's because it has a different objective now. We're talking about the mass of material at the site, and has that changed between the two time periods. So the null hypothesis is that the mean difference is equal to 0. The alternative, two-sided, is that it's not 0. The difference might be greater than 0 and it might be less than 0, and we want to test for both. Or we could specify only one of those directions and do a one-sided test if we have a reason outside of the data set to do that. If the mean difference is not 0, then the means of the two separate columns are not equal. We can say that their means are not the same. This test has more assumptions than the non-parametric ones. The primary one is that the paired differences, the column of differences that is computed, must have a normal distribution. And again, most of the data that we collect is likely to be skewed and not this way. So you should check this with a QQ plot. There is QQ plots for interval censored data. Remember I talked about those two columns, min and max, of differences. That's what's being used here. So there are QQ plots for that in survival analysis routines in statistical software. If the data are not normal, the p-values might be too high. This is just like any other parametric test. If you don't meet the test assumptions, the p-value gets pushed up and you will not see differences that are really there. They will not be pushed down and be too low. So they're going to give you false negatives in terms of the test results, not false positives. That's a characteristic of parametric tests. So if your p-values are low, 0.01 or lower, then the violation of the normal assumption has not obscured the non-zero mean difference if you see a really small p-value. But if the p-values are around 0.05 or higher, 0.10, maybe even 0.20, those are all in the range where non-normality can push the p-values up, even though there is a difference in the data. So then your alternatives are basically to do a non-parametric test. Here's a picture of that QQ plot. If you know, these are also called probability plots, and the straight line that's in the diagonal here is a representation of the normal distribution with the same mean and standard deviation as the data. And you'd like to see the data falling right along that straight line. This has a big curve, a big smile in it. And so it is not a normal distribution. So that could be a worry. You could try to do something like a transformation of the data. If you do that, what you need to do with paired data is to transform the original data columns and then compute the differences. So if you took logarithms, you would take the log of 2001, separately the log of 1996, and then subtract those two off to get a difference in the logs. Once you do that, however, whether it's the log or any other transformation, you're no longer testing for differences in means back in the original concentration units. And so it will not still be a test for differences in the means. You're no longer looking at this difference in mass. So here's the send paired command. And its p-value is very small. So there was a strong difference between the two sites. So the non-normality is really not a problem here, and you would not have to transform anything and not have to worry about it. It's very unlikely to see the differences that are seen here in the means. And it gives you a value for the mean difference, which is about 0.021. You can use these paired parametric tests, the send paired command, to test for not just two columns of data, but one column, and then one column that's represented by just a single number, a standard or a guidance value. So you can use this to test for whether the mean of the first column, usually it's applied in our situations, exceeds that standard. Again, this is something like a t-test, but for censored data. And so you're testing, it's going to be computing a one-sided lower confidence interval on the mean. This section 7b refers to the section in our Nondetects and data analysis class. But the idea here is that you're computing an LCL, and if you compute an LCL 95, then, and that value is above the standard, then you've shown in a statistical sense that the mean is above the standard. If you're just comparing the mean to the standard, that's not strong enough evidence in a statistical test because you're not taking into account the amount of data that you have and the variability. If you had only had two observations, you may compute a mean and it may be higher than the standard, but with two observations, it's very likely that it's not above the standard out in the field. So using a confidence interval allows you to take that uncertainty into account. And if it's a 95% confidence limit and the standard is below the LCL is higher than the standard, then the p-value for the test is going to be 0.05 or less. The alpha level in a test is directly related to the confidence in a confidence limit. So here's a picture where you have a mean and the LCL going down, a one-sided limit, and it is above the value for the standard here, and so we would say that the mean has been shown in a statistical sense to be higher than the standard. And you can do this test with this send paired command. So it would be like this, where you have the 2001 data and their censoring indicator, and then the value for the standard, just one number goes in here, with the alternative being greater if you're trying to say, does the data exceed the standard? You can say alt equals less and look for a value that's significantly less than the standard if that's the direction you're interested in. Maybe for dissolved oxygen that might be of interest, but most things we look at are exceedances on the upper end. So here the p-value is very small. We would reject the null hypothesis that the mean is at 0.01, and we would reject it in favor of the mean being above, being greater than 0.01. And the observed mean is greater, 0.036. And here it's significantly greater. That means that we know it's large enough for the amount of data we've collected, the amount of information that we have, that we can, in a statistical sense, show that it is higher than 0.01. So to summarize these tests for difference between matched pairs, they answer two different questions depending on whether you use the parametric or the non-parametric tests. And the non-parametric tests, the three that we introduced, are looking at whether concentrations are more often higher in one group than the other. So that's a frequency question. The parametric tests are asking whether the total across the whole site are equal to each other or not, and that's a question of mass. So you have to decide which of those tests are what you're really asking. You would choose the test based on your objectives, not whether on a data have a normal distribution or not. All right, that's our webinar for this month. Actually, it's not a webinar anymore, is it? It's a video sitting on our site. If you'd like more information on these matched pair tests, there's a little bit of discussion of them in the book that I wrote some years back, Statistics for Censored Environmental Data using Minitab and R. You can take a look at the other videos that are up on the site where this one is now sitting. If you know people that are interested in how to analyze data statistically with Nondetects, you can get a lot of information for free from these webinars. It's certainly just a fraction of what's in our Nondetects and data analysis class, but it's something at least. So you let other people know about them. Well, thank you for viewing today. Some of the materials based on that book that I showed you before. All of this is my own opinion and don't represent those of anyone else, of course. Thank you very much, and that's it for today. Bye.